Great talks so far. I hope everybody is learning a ton about how to profile and optimize their applications on different platforms. So in this talk today, I'll be talking about the ROCm tools that we offer for AMD platforms, and specifically focus on two tools which I think form the backbone of a lot of different other ROCm tools or AMD applications. So the ROCm profiler and the debugger. And both of these are part of the command line interface tools that come with your ROCm releases. But if you're interested, there is always more information that you can find that can be found in the official documentation. So let's get started first with the profiler. So as I said, it's part of the it's one of the command line front end libraries which come with AMD GPU and it is provided with the ROCm releases. So rocprof contains the central components allowing collection of different application tracing and hardware counters that you're interested in. And by looking at those, you can understand the performance of your applications. One of the nice things about rocprof is that you can visualize the output of rocprof, all the traces and all the timelines in the Chrome browser, which I hope everybody is using Chrome browser, by the way. So you can use that. To get started, rocprof command line is pretty simple to use. If you want to understand what are the different flags, like what is the usage, you can always use the -h flag or --help. But there are some very useful housekeeping flags, such as if you want to understand the kernel timestamps and like the timing of your GPU kernels, you can use the timestamp and say on or off. By default, it's off, so you have to explicitly say that you want to collect the timestamps. Similarly, the other is the base name. So generally, when rocprof is collecting the traces or your counters, and it is looking for your kernel names, it's going to extract the entire kernel name along with all the input arguments and everything. If you only want to look at the base name and don't want to look at the other things, you can have the base names on off flag again. And then one of the very nice flags that, in my opinion, is the -t flag, which allows you to change the directory where all the profiling data is initially dumped and then copied to your specified directory. So generally, it's dumped in the temp directory, but sometimes if you're working on some systems where you either don't have access to the temp directory or your temp directory is already full and you don't know what to do, you can always use this. Few ways to direct the activity of ROC profiler is by providing other flags to it or other options. One of the most common ones is saying that, hey, I'm really interested in collecting a few counters and I want only specific ones. So I can create an input file and I can pass that to the ROC profiler. And similarly, if I want to collect different types of traces, so hip trace to collect all the hip APIs and roctx traces to collect only the timelines or the traces around the region of interest inside my kernel. So I can use those options as well. And getting more into the advanced usage side, if I want to combine different counters and I want to start playing and calculating my own advanced metrics, I can create an advanced metrics in a XML format, and I can also pass that to the ROC profiler. So it's going to take care of everything. And with that one command line, it's going to collect all the different traces for you. So let's start diving into a few things, starting with the collection of traces. So rocprof allows you to collect a variety of trace event types. And essentially for all of these, it generates a JSON file that, as I mentioned, you can open in Chrome tracing in your Chrome browser. So if you're interested in collecting the hip APIs that are in your kernel and the GPU kernels, you use the hip trace mode. If you are interested in analyzing what are the CPU HSA calls, where HSA is the heterogeneous system architecture levels, so what are the signals that are being sent by the CPU to the device, you can collect the HSA trace. And like I said, for code markers, you can use around the region of interest, you can use roctx traces. So the usage is pretty straightforward, as I mentioned. To rocprof, if you want to collect a hip trace, you just say rocprof -- hip trace and your application along with its arguments. So it will output a JSON file. And what I'm showing in the top in the figure is a snapshot of a Chrome tracing open in the Chrome browser. Uh, and you can see that in this pane, the Chrome tracing has different components. So in the top pane, you have 3 different rows. The first is the copy, where you can see the different copy, the data copies that were happening between the device and the host. The second is the HIP API, and it tells you all the HIP APIs that were invoked. And finally, the third is the GPU, and where you find the details of your GPU kernels. The bottom half of that picture is basically, if you click on any of these particular sections, so say, for example, your kernel name, if you were to click on that, it would give you details of that particular kernel, the time it took, the duration, what was the data type, and all those kind of things. Actually, I think it would be easier if I use a laser pointer here. Yeah. Similarly, if you want to collect HSA trace, so I think this picture is a little better in resolution compared to the last one. But again, you can see on the left-hand side, you have different HSA APIs that is collected by rocprof. And then you can, if you go inside view options, it tells you that you can turn on the data flow, and data flow is basically these data type markers, which tell you what particular API is linked to what particular GPU kernel call and things like that. So I think that is also pretty nice if you want to understand how the different parts of your application are linked to one another. And of course, you can collect multiple traces that is together. So you can have HSA and HIP being collected at the same time. But beware, I think one thing that I didn't mention in the previous slide was that HSA trace is the slowest of all, because it is interrupting the CPU signals every time, and it adds a lot of overhead. So whenever you're doing that, make sure that you are aware that you don't want to interrupt rocprof while it is collecting those signals for you, or those traces for you. And similarly, you can collect roctx traces. So I think there is a particular example that you can open up with HIP examples, which are already online on our GitHub platform, I think. And one of the examples, I think, matrix transpose.cpp. I think the slide deck, by the way, will be available with you. So when you click on that, it should open up the source code, and you'll be able to see how to invoke these roctx traces and what needs to be added inside your source code so that you can extract information around the region of interest. And once you do that and you collect the trace, your timeline will show only the regions that you wanted to see, basically. So rocprof can, apart from collecting timelines and traces, it can collect hardware counters for you. To see a full list of these counters that are available in a given version of ROCm, you can always do rocprof, and then you can do -- list basic or list derived. So the derived list is mostly derived counters which are dependent on the basic counters, which are included in your ROCm releases, and obviously also available on your hardware. So the way you collect these counters is, as I mentioned before, you say to rocprof that, hey, I'm interested in collecting certain counters, and you can prescribe that in an input file. And for example, in my input file, I'll say that it will have different it will have different lines and groupings of counters. So PMC is a keyword which I think stands for performance metric counters, and it's a standard Linux lingo, I guess. And you can say that these are all the counters which are available inside these two lists. So you can always look that up. Now, one nice thing is that um, similar to other cases, we can't, like on our hardware, we can't collect all the counters in a single pass. So if, for example, you in your input file, you were to have that, hey, I want to collect all these metrics and all these counters, and you just have all of them clubbed together in a single line, it will obviously throw you an error, but at the same time, it will give you suggested groupings. So you can always use those suggested groupings, or you can always separate them on your own. And each line in the counter file is collected in one pass. And ultimately, a CSV file will be created, which will have all the information about these particular metrics related to your application. And we'll see more of this during the breakout session when I'll have more hands-on, I'll show a more hands-on approach to this. Very commonly used counters on our hardwares are the VLU utilization, where we want to check the percentage of our arithmetic or logical units being active in a particular way. If you have low VLU utilization, obviously it's due to some high divergence or poorly sized grid or things like that. So these sort of give you an insight into where you want to start looking at and start optimizing your code. And others are VLU busy, fetch size, write size. So fetch size and write size are also important because it tells you what is the total size of the data which was fetched or written to the global memory. L2 cache hit, memory unit busy, memory unit stalled. If you see that you have a high latency and you want to see where a lot of time is being spent, sometimes your memory units can be stalled. So this also gives you a good idea of that. And of course, a full list of all the available units either can be found by going back to those rocprof -- list, basic or derived, or you can also look them up here in this GitHub repository. Few things to note is that GPU hardware counters are global, so kernel dispatches are serialized, and only one dispatch is ever in flight. It is highly recommended that no other applications are running that use the GPU when you're collecting the performance counters. That's because, again, performance counters, they sort of interrupt your flow of instructions. And if you have anything running in the background, it's going to add on to those, to the latencies or like to the performance that you're seeing, and probably it won't be very accurate. I would suggest that use the base names on flag, because otherwise, if you're using, like in your applications, if you're using multiple libraries, so sometimes things can get haywire. Like, I don't know how many of you have started using libraries like Cocos and things like that. Like when you start combining these libraries with your application, the kernel names can explode, and then it takes up the entire view of your entire screen. So base names on is a really nice thing that I've figured. And some common questions that we always get is, how do you time a kernel's duration? So the timestamp on will give you 4 different times, which is the dispatch time of the kernel, the begin, end, and when it was completed. So the difference between the end and the begin timestamp is probably the closest thing to your kernel duration. There is another way. If you use the --stats with your rocprof, it will give a resultant file which will include which will include all the kernels and their statistics, including how much is there, like how much time was spent on the GPU by that kernel, and what is the percentage of, or like what was the occurrence of that kernel over time. And but one thing to note is that with this option, that time is aggregated over repeated calls. So if you're looking at a particular like for a particular dispatch, I think timestamps on is probably a better bet. One other nice feature is collecting the traces or counters on multiple MPI ranks. So if your code is using MPI and it's running on a distributed network, you can always use rocprof. And this is the syntax that you should be using if you want a single unified CSV file for all the ranks. If you don't do this, if you change the if you change the location of rock process, for example, you have MPI run before and rocprof after MPI run, it's going to produce different output or CSV files for each MPI rank. And if you're working on a large system and a large problem, that can be hectic. Currently, multi-node profiling is not supported, and I don't think I can say for sure when it's going to be available, but that's the case for now. So if you want to profile on multiple node runs, you'll have to launch rocprof on multiple nodes individually with your application. And one final thing about rocprof is the profiling overhead that I was mentioning. As you can see, if this is base performance of your application, which is normalized, and you run just basic rocprof, you have some overheads, obviously, because it's going to interrupt and it's going to start collecting different metrics and traces, right? But if you have HSA trace, you can see the overheads that it adds. It's more than 2.2 times, 2.1 times of your actual base performance. So it's really slow. If you, it's a really nice tool if you really want to understand what is happening with your device and what are the CPU signals and how things are being transferred. It's if this is your first time working on GPU, I think this is one of the best ways of understanding how CPU and GPU they work in synergy. And this was something nice that I tried when I was doing my PhD like 2-3 years ago. But again, beware that it takes time and you don't want to interrupt your GPU or your system while this is being collected. Any questions on profilers so far? That's I'm guessing it's a silent no, so I can keep going. So debugger is another nice ROCm tool, and from the tin, actually, when I say from the tin, I don't know how many of you know it. Back in the day, it used to be a slogan in the United Kingdom, which basically used, and then it became a very common lingo, which basically means name of something which describes its qualities. So I think it fits really nice for ROC GDB because its name has GDB in it, and ROCm debugger is a source level debugger for Linux-based GDB. It enables heterogeneous debugging on ROCm platform of an x86 host architecture along with GPU architectures, which is supported by the AMD debugger API library. And just like rocprof, the AMD debugger API library is included with your ROCm release. The current ROCm debugger or ROCm GDB is an initial prototype that focuses only on source line debugging and does not provide any symbolic variable debugging capabilities for now. The user guide has details of the features and commands that may be implemented in future sessions. So sometimes you get asked, is it similar to CUDA GDB? Yes, and mostly no, because ROC GDB is or will be GDB because it tracks the upstream GDB master, and that's the way that's the track it's taking. I see there is is there a question, or can I keep going on?
There is one question in the Zoom chat. So Samik asking, can GDB debug Python code?
Sorry, I didn't get that. Let me.
So GDB debug
yeah.
so Python code. Yeah, Samik just asked the question. Yeah.
Right, GDB can do Python code if I'm not wrong. Like, so to prepare your code for the debugger, you need to take a few key steps specifically on AMD devices. One of the thing is that you can use any optimization level when compiling the code. So you can use O3 for all I care. You need to have ROCm load all the code objects at initialization. So you can do that by exporting the variable hip enable default loading. And one key thing is that you need to add this flag during compile time, which is the -ggdb. So if if for example I'm compiling some code, I need to add this -ggdb to my compile um, uh, flags. And if you like while using GDB, if you want to see all the HIP APIs and like extra level of information, you can always enable that by exporting another variable, the AMD log level, and that will give you all the extra information about HIP API calls and so much more. So what all can ROC GDB do? Well, everything that GDB can. So you can see switching between different wavefronts on the device and seeing the info of what each of those wavefronts are doing. You can take a look at what the how the read and write to hardware registers is happening to the earliest scratch. You can add breakpoints, watch points. You can even do ISA level debugging. So you can dive into the assembly code, and you can start and you can map ISA to the source lines and see how, like as you are stepping through the code, how different registers and different things are being initialized and populated. So let's see a few of those in more detail. So I have an example code here on the left. And if I want to add a breakpoint to the host code, because ROCgdb is essentially GDB, when you launch that, it will give you a GDB interface, and you can use the same GDB commands. B for breakpoint, so you can say breakpoint, name of the source file, and whatever line of code you want to add a breakpoint at. So when you do that and you say run the application, it will add a breakpoint there, and eventually it will give you something like one particular thread hit that particular breakpoint. You can also, like I said, start looking at different uh, like variables that are or like how different pointers are initialized. So say for example you want to see the pointer device d_u, which is on the device. So you can see that because it's not initialized yet, if you just see p_d-u, it gives you the value um, or like the data type of that. So you can also add breakpoints to the device kernels of your interest. So say, for example, in this particular code that I'm showing, I have a kernel named local Laplacian, and I add a breakpoint to that, just like before. And I say that, yeah, keep continuing. So once you do that, it goes through and it continues, and then another thread hits that particular breakpoint. Now, when that happens, um, uh, you can see that if you keep stepping through different threads, if you can see the different numbers here on the right hand side, different threads are going to keep hitting that same breakpoint again and again, and GDB will switch context to those new threads every time you hit step. So if you want to understand this, like what is the like how are these threads labeled here? The first is the AMG, the agent target ID, with followed by the QID, the dispatch number, which basically tells you how many kernels have been launched till now. The wave ID number, and this is something good to know because you want to know how many waves have passed through or like and things like that. And finally, the work group or block index number. And these information probably is nice to look at because it tells you how or like what different wavefronts and what different threads are doing inside your kernel. But let's say, for example, you want to have the ISA and you want to dive into the assembly level code. So actually what I'm showing here is I'm combining ROCgdb with another application. It's called CGDB. It's a courses-based GDB tool. And when you do that, it gives you this nice pane where you have on the left-hand side, you can have your source code. On the right-hand side, you have the GDB. So anyways, with that, you can view your assembly level code by typing the command :sed this, and that will add all the assembly level instructions to your source code. And now when I step through, I can see what all different registers and what all different parts of the code are being worked on. So if I want to see what are the number of active host threads and GPU wavefronts, I can always do info threads. And with info threads, it will populate a list of all the different threads. And asterisk is basically the current thread that you're visualizing for which you have the source code or like the stack trace opened up. One question is, what happened to the rest of the threads? Why are there only so less number of threads? And actually the answer is that when you step through, most of the other threads and wavefronts have passed through, they've continued, but this particular thread is waiting. So that's why you only see the small number of threads here. You can switch again between different threads if you want to see their functionality. So you can say thread and whatever the number is, or the short form I think is just T space, whatever the number is. So for example, thread 2, and I can switch the context and I can start looking at those things. And like I mentioned, if you export the variable AMD log level 3, it will print all API calls and more that is happening. So compared to before, you can see that now on the right hand side in the GDB, it outputs all the different HSA APIs and HIP APIs and everything, which is as it steps through my source code. So yeah, ROCgdb has several other features that I have not covered in this presentation. There is a lot more. If you look at this particular user guide, it should tell you more details if you're interested. And along with your ROCm releases, if you go inside that, inside the share folder, you can always find more documentation for specific things that you want to look at. Now, these two tools have been more on the command line interface end, like we've been using mostly the terminal and typing these commands, right? Now, I think that these form the basics of what we have to offer and what other tools have to offer for us. For example, there is another tool, AMD New Prof. Now, this is more of a user interface. It has a nice graphical user interface. You can run your application, you can collect profiling, you can do some analysis, and it again provides you, like as you collect the profile, it will show you different hotspots. You can do different power profiling and things like that. So this is all nice, but again, in the back end, when it is collecting profile, it is basically going to be using your rocprof and things like that. So so I guess you can browse through those different things. I think one more tool, if you want to really focus only on the GPU side, is GPU Profiler. This is also open source, AMD. And a lot of you, if you have your local workstations where you have Radeon GPUs in your workstations, you can use this. And this is also a nice tool where you can look at the performance of your different applications and things like that. But again, as I said, in the back end, everything is going to rely on rocprof and ROCm debugger. So with that, I think we have a few minutes, I guess. Are there any more questions? Anything?
Yeah, there is one question in the Slack channel. So can you see the Slack channel? The track 6 breakout AMD channel. Ryan asked one question.
Did you say Slack channel or?
Yeah, Slack channel. So track 6 breakout dash AMD channel. This is dedicated to the AMD tools discussion.
Yeah.
So Ryan asked one question over there, and I don't know. The Samik asked about the GDB, if GDB can debug the Python code or not. But I don't know. Samik, did you get the answer about the question, or you can speak up?
Yeah, Suresh, thanks. I just posted a question on the chat. My question is with regards to this sort of a framework where you have Python, which is wrapping around C++. All right, okay. So I just got that answer on the chat. So apparently it's total view. So basically, I want to know if there is a debugger which can seamlessly transition between Python and C++. So
okay. Yeah, I mean, I've not used total view, so I can't speak for it. But
yeah, how about the AMD side? AMD side, do you have any tools for that purpose? I mean,
for AMD side, we like specifically in my team, I want to say we've been relying on the basic tools that I was talking about right now. Obviously, there are other tools that people have picked on. I don't work specifically on Python related stuff. All the applications that I'm working on or have been I've been voluntold to work on is I'm related to C++ or Fortran. So for me, these basic debuggers and profilers, they work the best.
I got it.
Yeah.
Samik, so go ahead. Sorry.
But I know that there are a few people who work on things like, for example, PyTorch or TensorFlow, and I've not heard them having issues with these debuggers. But maybe I'm wrong. I can't be sure about it.
Okay. Yeah, Samik, I think after lunch we will have the cross-platform session, right? So DDT and the Total View, both of them are debuggers available on multiple platforms. So I think your question, you can ask this question again to Ryan and Nikolai at their session. So yeah, thanks for asking.
Yeah, sure. Thank you.
Siyash, can you see the question from Ryan on the Slack channel?
Yeah.
So we have 1 minute, so you can answer that question.
So Ryan asked, do you profile or debug OpenMP target offloading code similarly to HIP, or is there a separate path? So OpenMP offloading, like I know a few of my team members have been working on that. We've been using similar tools to do that as well. Yeah, I don't remember if there is a separate tool to specifically work on OpenMP targets on our devices, but like I said, because GDB and ROC Profiler, they are so basic, I think you can use that. And yeah, and I can always reach out to my teammates. So I'll be available on the Slack channel, and if there are any pending questions, I can always keep answering them. But yeah.
Okay, thank you, Sash. Yeah, so it's great timing, and yeah, thanks a lot for presenting really nice overview of the ROC Profiler debugger. It's really nice talk. So I think this is really a good starting point for the AMD tool sets for the AMD GPU. So yeah, thanks. It's great. So from now on, we are moving on the parallel breakout session. So let me share my screen here. Okay, so yeah, so we have 3 breakout sessions. So breakout room B, we will continue the Intel V2 advisor hands-on session, and you can leave any question here, track 6 breakout in Intel, and then the Kevin will answer your question. And also you can talk with Kevin in the breakout room B. And for NVIDIA session, we will have the breakout room C for the NVIDIA hands-on session. So Max will continue the nice example.